Okay, the last data resource in the Year 13 data book is a really good resource to use to test to see if you can actually look at what you're given and work out what's going on. Most of the answers can be got from either the text or the data that you're given. So we'll start off with, so it's about oestrogen. It tells you it's produced by an enzyme, and the enzyme is called aromatase. It tells you that the main source of oestrogen is the ovaries. So that piece of information is important. So oestrogen is produced by an enzyme, and that enzyme, most of that is made in the ovaries. It also tells you how oestrogen can work. So it can stimulate some oestrogen working causing tumours. So what it does is it binds to oestrogen receptors on the cell surface membrane. Okay, so that could be a potential way of stopping that from working, is you could perhaps block the receptors, stop them from binding. Another way potentially you could cause oestrogen to stop being produced is somehow to inhibit this enzyme. So there's two potential different ways that you could stop oestrogen causing tumours. You could inhibit the enzyme, so less is produced, or you could block the receptors so that the less oestrogen can bind to the receptors. So let's look at the second paragraph. You can see here, again, I've put a lot of annotations around the outside because these are things, answers to questions can be got from within here, or the sources of how you get to the answers. So first of all, so they're testing two drugs, how they could prevent lung tumours. So they're using mice. So mice are not humans. So if you look at the AO3 questions at the start, if you're using mice, they are similar to humans, so they've got similar physiology, but they're not the same as humans. They have different physiology, so drugs could react differently to mice than they do to humans. So that, if you've got an evaluate question, that would be an against point or a negative point. It tells you that they remove the ovaries, because what they're wanting to do is to look at, see if it's the estrogen produced in the lungs that causes lung tumours. So they have to get rid of the main source of estrogen, which it tells you up here. So they've got to remove the ovaries. So that allows you to see if it's estrogen produced in the lungs that causes lung tumours. So they have to remove the ovaries, which is the main source of estrogen. It also tells you that they used random samples, and this avoids bias. So that's a good point. So that's a tick in the favour of agreeing if there are any conclusions that can be made. So that's a good thing. However, they're then going to ruin that with having only 10. So a sample size of 10, that's very small. So it's not representative at all. So the drug could behave differently in other mice, and we don't know because the sample is not representative. So this tells us a bit about the drugs that we're looking at. Do not get bogged down by the names of the different drugs. I'm not even going to try and pronounce them. But what you need to break this down to is we've got one with a placebo, so neither drug. We've got drug R, drug S, and then we've got group T, which has got both of those drugs. Okay, so it tells you here that this enzyme inhibits the enzyme aromatase. As we went through before, that's going to cause less estrogen to be made. If there's less estrogen made, less can bind to the receptors, less tumours. This one here binds to the receptors themselves, so they could block. So these are going to block the receptors if they bind. Less estrogen can bind, less tumours. So in theory, that's how it should work. So let's look at the data then. So what data have we got if we're going to evaluate which drug is better, or should you use both at the same time? So first of all, so when you're going through anything that could be plus or against, for or against. So first of all, they're only looking at 15 weeks. Okay, that is not long term. So you've got no evidence at all if either of these drugs work in the long term past 15 weeks. It can take years before a drug can work. Here we've got mice again, not humans, different physiology. The drug could react differently. So what we're looking at here, so group, this is the control, this is what we can compare the other results to. You can clearly see here that when both drugs are used at the same time, we've got the least tumours. So we've either got 0 tumours or 1 tumours. And if you compare that with the rest of the groups, there's a lot fewer, again, comparative language, fewer tumours when both drugs are used. So that's a plus point in the favour of using both at the same time. If you look at this graph, there's a lot can be got from this graph, and apologies for all my scribbles that are on here, they're quite hard to tell in the video, but I'll talk through it. So first of all, a couple of things that we can look at. We've got range, not standard deviation. So range isn't as good as standard deviation in some ways because range doesn't show you the spread around the mean. Range is affected by outliers. So it could just be one mouse, for example, that gives this result to be all the way up here, or one mouse that could cause the result to be all the way down there. So standard deviation is better because it shows the variation around the mean, and also standard deviations can be used to see if you've got a significant difference or not, if they overlap. However, if ranges do not overlap, that shows you that every single individual was greater or less than the other ones if they don't overlap. So it can be better, but there's no standard deviation. That's something you can comment on. So no standard deviations, you don't know if the differences are significant. As well, another reason we don't know the differences are significant, there's no mention of any statistical test. Ideally, we'd want a t-test in here because we're comparing means. So there's no statistical test carried out. We don't know if the results are due to chance, if the differences are due to chance. So we cannot prove if there's a significant difference or not. So first of all, let's look at some agree points. So what have we got? So we've got the red pen here for some agree points. So we've got white. So we're trying to agree, does using both cause, is that the best treatment? So here we've got the lowest mean, so that's a plus point. So the mean is lower than either of these three, so the tumours are the smallest after treatment. We've also got the lowest top of the range. Okay, so lowest top of the range, so the smallest, so they're generally smaller than the other three. So that's 2 plus points. Smallest mean, lowest top of the range. However, the means are actually quite similar. So that's, I've drawn a square bracket on that's not very easy to see. So a square box, I should say, rectangular box around these four. So the means are all fairly similar. There's not much difference in the mean values at all, so that's an against point. Also, the ranges overlap. So this does mean that in some situations, for example, the tumours here are bigger than the tumours there, there, and there. So again, that's an against point because the ranges overlap. You can't tell if the difference is significant from it, but you can say that sometimes the tumours are bigger when both are used than they are in either of them separately or the control.